you probably don't want to write this down because I've already posted this, but there's a lot of things here, and I'll just be talking about this because this is more or less like a table or a empirical relation. So okay, so it's posted, but I'll go through this quickly, and the goal here is to solve the problems. Okay, so I said earlier that the endurance factor SE is not the same as SE prime. SE prime is the one which you compute when you do this experiment in the lab, right? So it's nicely finished. The operating temperature is controlled, and so on. Okay, but when you take this on an actual machine element, you'll see that the temperature would be different. It won't be properly finished. The finish would be different. There are differences within the size and so on. So to account for that, we have these factors Ka all the way to Ke, which you need to compute and then adjust the Se prime such that you get the corrected Se. So Se is the endurance for the actual machine element, and Se prime is the lab tested specimen. So Se will be lower in value than Se prime. That is, these factors will diminish the strength of the material, right? And so you see that these factors are less than 1, right? So they hurt you more than help you, which is understandable, right? So if you have a very well polished material, you'll see that Se will be less than Se prime Se prime will be greater for a well polished material. It's a specimen. Se will be lower than that. Okay, so these factors, there are 5 factors, and there's another one, miscellaneous, we'll forget that, A, B, K through Ke. Okay, so what this session will be basically talking about these factors, and again, these come from empirical experiments. So what you do is, instead of loading the specimen with a perfectly polished specimen, you load it, you make it go to failure, then you change the surface finish, and then you redo the experiment, and then you get a new value for Se prime. That's one way to do it. Or what you can do is you can basically, once you get this Se and Se prime, so now Se prime comes from the test specimen, Se comes from the impure or whatever factor you're considering. The ratio of the two will give you K, and that's how they came with this relation, which again is an empirical fit based on SUT. So all you do is figure out what the surface finish is. There are 4 of them, and then that will give you what the surface factor is and what the exponent B is. Once you have A and B, you'll put it in that expression, and you have a K. Then that K you will put over here, and that will tell you the new Se, which is now going to be less than Se prime. Right. So so this is just one factor, and then if there's another factor, like say for example, size factor, then you'll use Kb and then Kc. So you need to figure out what are the factors which are different from the laboratory specimen. So that's just one. Here's the second one. Size factor Kb. Okay, there are two setups here. One is you have a rotating, let's call that 1, rotating round specimen. So the specimen is rotating like the experiment you saw. Within that, there is bending and torsion, and there's axial loading. So for bending and torsion, Kb is a factor, and you have to use those expressions. This depends on the diameter of the specimen, which is D. I have that here. So D is the diameter. If it's axial loading, then the size factor doesn't matter. That's why Kb is 1. Okay. Then part 2 is a non-rotating specimen, a round or non-round specimen. Okay, so there is a theory called critical volume theory, which tells you how to compute this factor for KB in case of a non-rotating specimen. I've put that in notes, but there is no real need to go through it in waste time. So I'm just going to skip all that. What comes from these, eventually these things, is a factor KB, which is, by the way, let's see what's KB. So what this does, this theory does, is basically gives you a effective diameter D. Okay, and that is based on that theory I talked about. So once you get the effective diameter, you then use the same expressions you have over here in order to compute KB. So compute, so by this theory, compute D and then use 1 to compute KB. Okay, so that we'll do that in a bit when we solve a problem. Okay, and then that just gives you D's for, this one doesn't give, this one just gives you A's, but D can be found, it's basically pi D squared divided by 4. But don't worry too much about these two, they're not very important here. Okay, then there's a loading factor Kc, it depends on the load. For bending, it really doesn't affect, so this Kc is 1. However, if axial loading and torsion, then this Kc is less than 1. So axial and torsion reduces the endurance strength for loading factors, but not for bending. So Kc, Kd. Okay, Kd is an important factor, temperature factor, and I think it's very important because in the when you're operating the machine, you have a different temperature from what the test specimen was actually was the temperature at which the test specimen data was collected. So Kd accounts for that. So what we do here is there's again an empirical relation between St, which is the ultimate strength at operating temperature, and ultimate strength at room temperature. So this is for the specimen. Right, the specimen is always tested the room temperature, but temperatures might be different when you actually load it. So what you do is you figure out what the temperature is in Fahrenheit or Celsius, then compute this ratio St divided by Srt. Okay, now there are two cases. So this is case 1, and then there's case 2. So case 1 is when Se prime is unknown. Okay, so you will not have Se prime available to you. In this case, what you do is you first estimate, just call this ABCD. So first estimate the ratio St divided by Srt. From there, you know what the temperature is, and so you can compute that. Then compute SUT, this is the ultimate strength at the operating temperature, not the room temperature, using a simple ratio. So maybe a better way of writing this is follows. SUT okay, so this is known because you computed it. This should be RT. Okay, and using this ratio, now you're computing the ultimate strength. Now, ultimate strength at room temperature is again known. That's something which is provided to you in tables. So you can compute SUT at temperature T. That is the operating temperature. So once you have SUT T, that goes inside these equations. And then you get Se prime. So we've seen this equation for Se prime, just that SUT now is not at room temperature, but it is at the elevated temperature T. So if you like, you can also put it this way. So like, same for all these. Just makes a lot of clutter, so I just skip that. Okay, so if you do this way, then KD is 1 because you already accounted for this adjustment. You already adjusted the SUT based on this ratio. So you don't have to do anything with the ratio KD. You just get SE as SE prime and you proceed. And I'll do a problem where it will illustrate this, where we have two cases. Okay, that's case 1. In case 2, SE is known. You're given SE known, SE prime, in which case you do the same computation, ST divided by SRT, which is a formula given here. So you know that. That's step A. Then estimate KD. It's just the same as this ratio. And then step C is KD is now known from step B. SE prime is known. So you can sub that here. And so you have SE. Okay, so that's for temperature. And then the last one is reliability. How reliable is your machine element? Depending on the reliability, how is reliability computed? There is like this whole thing about in industrial engineering is about estimating how reliable a component is. Basically, you depending on the kind of machining operations, you can make a prediction how reliable it is. So this is considered to be very reliable, and this is considered least reliable, which means 50% means that every 2 times you use it once, it will fail, which is not good. But 99.999 means that if you move the zeros, well, this might be easier. So after, if you use it as element 100 times, it will fail once. And that's why it's 99% reliable. So the greater this reliability factor is, the more reliable it is. And so what you do is, in order to find that how this affects this endurance limit, you can either get ZA, which is given here, ZA, or it actually also gives you KE directly. So either use this formula with ZA or directly use KE from the last row. So this is actually redundant. You can just base it off this. The smaller it is, the smaller the K value means it has more strength, right? The bigger the value, the bigger, so it's SE is KE SE prime. So the smaller KE gets, the lower the strength is. Which I thought would have been other way around, but apparently the bigger the reliability is, the smaller the value is, which means that your strength is going to decrease as you make it more reliable. 0.6, right? Okay, these are again empirical relations. Okay, so let's put all this together in a few problems. Okay, and I think that's the best way to learn about these factors. Okay, so a steel specimen has a minimum ultimate strength of 520 MPa. So SUT is 520 MPa. Okay, here's a key piece of information. It's a machined surface, and we need to estimate Ka. It's just it's just what do you call finishing process where you probably sand it or something like that. Not sand it, it's done on the machine. It's very general, I know that. Yeah, it's not very specific. Like hot rolled is more specific than machine. Okay, so since it's Ka, let's go back and look at what we have for Ka. So for machined or cold drawn, so by the way, Ka is A times SUT to the power of B. SUT is given in, and I forget this, in MPa, so SI units. So MPa. So we need to use this formula, but we need to get A from here. This should be our A, and this is our B. And so we just have to use that formula to get Ka. Okay, so from table, Ka equals, so A equals 3.04, B equals minus 0.217. So Ka equals A times SUT is to P. .04, 520. So Ka is 0.78. So just saying that 78 is almost like 0.75, which is 3/4. So it's decreases by a factor of by 25%. Just machining the surface. That's the answer. No, yeah. So remember that SE is Ka SE prime, and so whatever you have SE, that is the test specimen. Because of the fact that this is machine surface and the surface finishing is different from the test specimen, you will see that the Ka is decreasing SE by a factor of 0.78, which is not good because now your strength has decreased because of this particular finish. Right. Okay, so here is a more a better problem than that one. Okay, so the shaft is loaded in bending. It has a 32 mm diameter and a filleted shoulder of 38 mm. So what does this mean? Well, this means that it's something like this. So this is the 32 mm diameter, and then since there's a filleted shoulder, it probably means it's something like this. This is 38. Okay, so something like this would have stress concentration because of the fillet. It's not important in this problem, however. Okay, estimate the size factor KB for rotating mode, non-rotating mode. Okay, so let's see how to solve this. So the diameter D is 32 mm. Okay, and then go to the table for KB. Okay, so the first one is in IPS. We don't want that. We want the second one in mm. Just copy this whole thing. Okay, so the diameter of 32 mm falls here within this range. So we use the first. So this is, by the way, part A for the rotating mode. This is for, write it down. A, so this KB is 1.24 T raised to minus 107. They are non-dimensional, right? They don't change the dimensions because it's, remember, it's SC equals the K times SC prime. So units of SC and SC prime are the same. So K has to be non-dimensional. That is 0.86. 0.86. 0.858. Okay, so there's an ambiguity here, right? There is a 32 mm diameter, 38 mm diameter, and so which one do you use? I use 32, and I'm using 32 because of the fact that I'm assuming that well, we know that the smaller the diameter, that part will fail first, and the one which is bigger, and so because that's the case, the critical stress would be in the 32 mm, and that's why I'm solving KB based on that. But if you solve it based on if you solve it based on 38 mm diameter, you'll see that the KB is actually lower than this value. Okay, but when you do the calculation, eventually you'll see that it's this one which matters more than the 38 mm, because if you remember, the stress is inversely proportional to the diameter cube or something like that. So the diameter has a bigger effect than the marine factor KB. Yeah, but to be actually, you should do it both ways: get KB, solve for stress, and then use the one which is a bigger stress for the failure, right? So that would be the right way. Here, there's a sort of inherent assumption, but this is just illustrating how to compute the factors K, KB. When you put it all in a problem, then you'll have to make that judgment. So don't worry too much about using 32 versus 38 for now. So when things fail, you want to use the bigger stress as your determinant of failure, right? So if there are two 32 mm, 38 mm, if the stress in one is higher than the other one, the 32 mm will fail first, then the 38 mm. Okay. So that's why you want to use the smaller end. Okay, so that's the calculation in rotating mode. And then non-rotating mode, we know it's a circular diameter, so let's go. So that's rotating specimen. For non-rotating, we need to go to this table. Okay, so it says that you need to adjust the effective diameter if it is non-rotating. So the effective diameter is 0.37 of the diameter when it is rotating. So 0.37 times 32 in this case. So DE is 0.37D. Which is 0.37. D is 32. That comes out to be 11.84. Okay. Now, when you compute the factor KB, you will be basing it off D equals 11.84, not 32. Okay, so if you use 11.84 in from here, you see that, and this is by the way mm. It should be the same one as before, same equation, 1.24. Now DE 107, so 1.24. Sorry, 11.84. That comes out to be 0.95. Non-rotating element, that's why we are changing that. Right. Okay, so what's going on here? Well, KB for rotating, this is rotating, and this is non-rotating. So you can see that, so KB for case B is greater than KB for case A. In other words, what it's saying is that if you are not rotating the specimen, it's going to be, it'll have a higher endurance strength because the KB is greater than for rotating. So clearly, if you rotate, probably it adds more cycles, or it's related to more fluctuations than non-rotating. So non-rotating would be more stronger than rotating. Okay, so let's get into more problems, which will now, it's going to get a little bit more complex now. So 1035 steel has a tensile strength of 80 kpsi, and is to be used for a part that operates at a temperature of 750 Fahrenheit. Estimate the endurance limit, which is they're asking to compute SE at the operating temperature if, so the operating temperature, remember, is 750. If only the tensile strength at room temperature is known, at the room temperature of 70 F, that endurance limit for the material is found to be, by test, to be SE equals 39 kpsi. By the way, something is clear here, that the room temperature RT is 70 F. Okay, the operating temperature is 750 F. What else? So the first part assumes that you only know the tensile strength at room temperature, which means that you know SUT at room temperature. In other words, that is SUT at 70, and that is 80 kpsi. And then this is for part A. And for part B, the endurance limit is given at, so SE prime is given, it is 39. Oh, this is endurance limit at room temperature, which is 39 kpsi. Okay, so this is, as I said, this is very algorithmic. You just have to go back to the table and go to that notes and then figure out how the temperature factor affects computation of KD. So it seems that you need to first compute this ratio, ST divided by ST divided by RT, right? Once you do that, you have two cases. SE prime is unknown and SE prime is known. Okay, clearly B falls in this one where SE prime is known. And question A is case one where SC prime is unknown. So we just have to go through that step by step and solve the problem. So as I said, first thing we need to do is compute these two things, not just one thing. This is in Fahrenheit, this is in Celsius. So we need to use the Fahrenheit formula. Let's just take this formula. Copy. And I'm just going to use this to first compute this ratio and then proceed to solve part A or part B. Okay, so T is now 750. SRT is 70 equals 0.98 plus 3.5, 10 raised to negative 4. The temperature in Fahrenheit is 750 minus 6.3, 10 raised to negative 7, 750 square. So S 750 equals 0.89. Okay, so we've done the first part. Now let's do case the A and B. C prime is unknown. Yeah. What's TF? Is it always going to be 750? No, in this problem, it's given that T is 750. And then RT is room temp, RT is room temperature. Okay, so let's just do it one at a time, and then we should have the answer. So let's go back and see this. Okay, so if SC prime is unknown, first estimate this ratio, which we've already done, it's 0.89. Then use SUT, then compute SUT at operating temperature using this formula. So the ratio of SUT to SUT at room temperature is whatever we had computed. There's a mistake here. This should be ST. My bad. It should be the same as that. Let's go here. Yeah. You're not given that in first part. In second part, you're given that. So just put a different number. This is 1. So A is ST, SRT is 0.89. We've computed that. Step number 2 is we compute SUT T divided by SUT at room temperature is equal to ST divided by ST, which is 0.89. And so we can compute SUT at 750 equals 0.89 SUT at 70. But we know what the ultimate strength at, we already know the ultimate strength at 70, it's 80 kpsi. So this is that is 71.2 kpsi. So we've got the ultimate strength at 750. We know the ultimate strength at room temperature, which is this. So once we know that, so step B is done. Let's go back. Yeah, step C is to use these expressions. Either, so first of all, we want this in IPS, and so we need to go with the top one. Is the ultimate strength less than 200 or it's greater than 200? Now we're looking at not the SUT at room temperature, but we're looking at SUT at the elevated 750 temperature. So we've computed it to be 71.2 kpsi, and that falls in this range. So we need to do 0.5 SUT to compute SE prime. So this is step C. Since SUT at 750 oh, so from here. That's given. It's a bit of confusing notation. You need to get a hang of S. Oh yeah, so yeah, it's a subscript. Yeah, so that's 71.2 kpsi, which is less than 200 kpsi, and so we can compute SE prime as 0.5 SUT, which is 0.52. to 35.6. By the way, I should just write it as this. Let me write it as SC prime. Everything we're computing here is at 750. SUT at 750. SC prime at 750 is half of 71.2, which is 35.6 kPSI. Okay, and then let's see what the last step is, which is, okay, so it says that if, so this is C, this is D. So D says that if that's true, then KD is 1 and SE is SE prime. So we pretty much solved for SE. So this is step D. KD is 1, and so SE is SE prime. And so our final answer is SE at 750 is SE prime at 750, which is 35.6 kPSI. We've already accounted for KD through this calculation. We've already accounted for the temperature. We've already adjusted the SE based on temperature. So why we adjusted it, you see this expression. This expression here adjusts for the temperature. So we already got the ultimate strength at 750. And so since we already accounted for the temperature, KD is for the temperature, right? We already accounted for it. We don't really need to do anything here. It's already been taken care of previously. That's all. Okay, let's solve the second part. The second part is if you're given that at room temp, so the endurance limit for the specimen is SE prime is 39 kPa. So we're given SE prime. So this falls in the second scenario. SE prime is known, and it is 39 kPa. Okay, so what we are given here is actually we're given at 70 degrees. So this is at room temperature. So I need to just put that down so it's very clear. So this is SE prime at 70. Okay, so we just go back to this algorithm and figure it out. So SE prime is known. Estimate ST divided by SRT. We've already done that. It's 0.89. Estimate KD. KD is that ratio. It's 0.89. And then I just estimate SE as KD times SE prime. So it's fairly straightforward, the second part. So A ST divided by SRT is 0.89. We computed that. Step B is estimate KD, which is ST divided by SRT, is 0.89. And then part C says, in order to get SE, at 750, we do KD times SE prime at 70. So 0.89 times 39. 35 kPSI. This one, okay, let's read it. So 1080 hot rolled steel bar has been machined to a diameter of 1 inch. It is to be placed in reversed axial loading of 70,000 cycles to failure in an operating environment of 650 Fahrenheit. Estimate the endurance limit and fatigue strength at 70,000 cycles. So that's this. This is one thing we want to solve for, and then the fatigue strength. Assume the reliability for the endurance limit estimate to be 99% and ultimate tensile strength SUT at 70 F to be 112 kPSI. Okay, so let's just try to distill whatever we've been given here, and that will inform the next step on as to how to solve this problem. So we are given the number of cycles, so that is n. N is 70,000 cycles. We're given SUT, and that is at 70 degrees, which is the room temperature. It's 112 kpsi. We're given the endurance limit, which will somehow factor into the endurance calculation. And we are asked to compute endurance limit. So SC and fatigue strength. Fatigue strength is SF. Yeah, so we can think of it backwards. So try to figure out what SC depends on, and once we know what SC depends on, we can then do other calculations to compute SE, and same for SF. So for one, we know that SE depends on clearly SE prime, and then KA, KB, KC, KD, KE. So it's part one. Okay, so let's just try to get each of these factors and SE prime, of course, and then we can solve for SE. Okay, so then what I did was I gave you this sort of a handout, which is posted. It just gives you ways to compute all these factors, but before that we need SE prime. I believe that was something which was covered previously. SE prime depends on SUT, and they can find it. Yeah, there it is. Okay, so SE prime is found from these expressions. Recollect that this was in PSI, KPSI, so we need the formulas here. So I'm just going to copy paste that, so you know you have a reference. Copy. Okay. Okay, so SE prime is clearly, so since SUT is 112 kpsi, it is less than 200 kpsi in this formula. So this is going to be 0.5 SUT, which is 0.5 times 112, which I think is 60. Okay, so it's 56. Okay, and okay, now let's get to K, KB, KC, KD, and KE. Okay, we again go to this handout I gave. K. Okay, Ka is A times SUT raised to B, where SUT is given to us, and we need to figure out A and B based on which of these factors, which are the surface finish. So let's check the surface finish. It's a hot rolled steel bar. So we go back to this and check for hot rolled. So SUT, we want this in kpsi because SUT is given kpsi. So 11 is A and minus 0.65 is B. And so let's put that in the formula. Ka is A, SUT raised to B. Let's work it out. Huh. Interesting. So what I forgot here to do is, and this is something which you probably should do before we actually compute these, use these equations, is since there's a temperature involved, I completely skipped this. 650, and these ones are given at room temperature. Well, this formula is for room temperature. This is actually going to give us at 70, right? What we want is SE prime at what temperature? 650 Fahrenheit. So what needs to be done is, and I skipped the step, which is we first need to adjust the SUT at 650. And then once we get SUT at 650, and that's what we'll use to compute SE prime at 650. So this is not incorrect. This is just a SE prime at 70. But what I'm saying here is that we're interested in computing this at 650. Okay. Okay, so what we'll do is first we'll see what the temperature effects are and then backtrack and solve this. So I should have done that first. This was not incorrect, just that we don't care about SE prime at 70. So let's do that calculation first. So let's try to understand the effect of temperature first, which is right here. Okay, so what we need to do here is first figure out what this ratio is, ST divided by SRT. The first one is in Fahrenheit, TF, and the second one is for Celsius. We take that formula, compute this ratio. Once we get that ratio, we will then compute the adjusted SUT at temperature T, given the value at RT, which is room temperature, and then just proceed, depending on which of those cases we have. Case one, when SE prime is unknown, which is the case here, and then the second one was known. So let's take this formula and start from here, though.
Represents
Fahrenheit.
What temperature is it? It's the room temperature, or is it
This is the ratio of S at T divided by SRT. RT is room temperature. So you just put the temperature with respect to, you just put the absolute temperature in Fahrenheit. So with room temperature, you'll put TF equals room temperature. If you want the factor at T, you put 750 in this case. T is 750. Okay, so let me just take this. Okay, ST Okay, that comes out to be 0.94. Okay, so we've got that. Okay, now we are in this regime when SC prime is unknown. And so we estimate that, we've already done that, it's 0.94. We want to estimate SUT at T. So T is now 750. And we know SUT at room temperature, which is 70 degrees, right? So I'm going to use this formula here. This was step 1. Step 2 is SUT T UT at room temperature is ST 0.94. And so SUT at 750 is 0.94 SUT at room temperature, which is, sorry, this is 650, my bad. So 0.94 times 112, 105. Okay, now we can compute SC prime at 650 is 0.5 SUT at 650. So 0.5 times 105 equals 52.5. Okay, so that knocks down one of those many things we need. Next is Ka. So I just copy it from there. It's Ka is A times SUT now at 750, 650, sorry, raised to B for hot rolled steel. So that is the table 1. So 11 for A and minus 0.65 for B. And minus 0.65. $52.5. .65. Okay, I need to compute that. .83. So 0.83. Okay, so KB. Okay, what is KB? If you go back, KB depends on, well, so first of all, we have rotating and non-rotating. Which case is this? So let's go back and see if this is. So it doesn't really give anything about rotating or non-rotating. You can just assume something. Let's just assume it's rotating. Okay. So assuming it's rotating, we have these factors. Now, is this bending, torsion, or axial loading? I forgot to check that. Let's see if it's which of those cases it is. Axial loading is right here. So we need to use the factor for axial loading. So go there. Assuming it's rotating, we use the axial loading factor. KB is 1. So 1. So axial and rotating. Okay, then KC. KC is the size factor. So this is a round specimen. And what else do we have for this KB? I think there's a table here. Oh, there it is. KC is 1 for bending, 0.85 for axial, 0.59 for torsion. So we know it's axial, so 0.85 for KC. Okay, then KD. So for KD, we go back to this thing. We were, in this case, SC prime is unknown, A, B, C. We went through A, B, C, we compute SC prime. Now, KD is 1 if SC is SC prime. So this is the case. So KD is 1. SC prime was unknown. Okay, it's still one more factor away, which is KE. Going back. Okay, so we were told that it's 99% reliability, which has a KE of 0.814. So KE. Well, let me just move all that to this page. Okay, now we are ready to compute the first part, which is SE. It's KE, KB, KC, KD, KE, SE prime. So that's 0.83, 1, 0.85, 1, 0.814, and SE prime is 52.5. This would give me, to compute this. It's 30.15. That's the answer to one of the questions, one of the two questions. Okay, the second one is asking us to compute SF. And we know that SF for finite life is given by the formula A time n raised to B. Where n in this case is given to be 70,000 cycles. Okay, so we need to figure out A and B. And A and B are given by these formulas. F S U T square divided by SE, and P is 1/3 log, so it's the not log 10. So log SE divided by FSUT. Okay, we have computed SE. It is 30.15 right here on top. And SUT now, SE is at 650 Fahrenheit. We also need to use SUT at the same temperature, 650 Fahrenheit. So SUT is something we've just computed right here. SUT at 650 is 105 kpsi. So we need to use 105. Okay, what remains here is just this factor F. And to compute factor F, we need to go back to the previous, I think 2 or 3 lectures back, where we had, there were 2 ways to compute F. There was either a table, sorry, a graph where if you know SUT, you can compute F, or you could use these formulas, okay, to compute F. So in this case, SUT, I think it's off the charts, SUT, the SUT is 105. Okay, so it's within the range. If we go back to this. Yes, sir. So it's 105, right? 105. Somewhere here. So it's like closer to 0.84. We can just assume 0.84, or if you like 0.839, 838. Just let's assume 0.84. Okay, so 0.84. The graph of F versus SUT, we get you can also use the formula I have there, and you get the same answer. Okay, so F is also known now. So we'll compute A and B. And once you get A and B, it's just a matter of putting it in this formula. So A is 0.84 times 105. This needs to be squared, divided by SE, which is in 30.15. It's 258. And then B is a third log SE, which is 30.15 divided by F times SUT, which is 0.84 times 105. Okay, minus 0.15, almost 155. Okay, so SF is A times N raised to B, which is 258, and is 78,000. B is minus 5. $45.75, 77, 78.